Welcome to Duo Security. Hello, ladies and gentlemen. Hello. Welcome to Duo Security. Thank you so much for joining us tonight here for Duo's Tech Talk. Tonight we're featuring Professor Paul Resnick from the University of Michigan School of Information. Paul was a pioneer in the field of recommender systems, which guide people to interesting materials based on recommendations from others. The GroupLens system he developed was awarded the 2010 ACM Software Systems Award. Tonight, Paul will present his recent findings on RumorLens, a suite of interactive tools designed to help journalists and the general public identify rumors on Twitter. We will be live streaming, so for those of you guys who are watching us on YouTube, please make sure that you use the comment section to let us know if you have any questions. And if you are on Twitter, please use the hashtag DuoTechTalk. For those of you guys who are here in the office, we ask you guys to use our lovely catch box to ask questions. Sorry, it doesn't get as reckless as that. So without a further ado, please join me in welcoming Professor Paul Resnick.
So thank you. It's great to be here. You hear me okay through this? It doesn't sound mic'd the way hers did. But you all can hear me, and he'll tell me if they can't hear me out in internet land. It's great to be here. I just feel like I'm in Silicon Valley.
It's where you're standing.
It's where I'm standing.
Speaker right behind you. No, that speaker's not on.
I feel like it's great, like I'm in Silicon Valley. There's a couple thousand companies at this size and growth, but it's nice that we have some here in Ann Arbor, and it's great to get out of the university and come here. I look forward to meeting some of you after the talk. This is not a hardcore security talk. It's not a security talk at all, but they invited me, so I said yes. And it was advertised what it's going to be about, so I hope you're all getting what you came for. I have a lot of collaborators on this project, and I will try to mention some of them as we go. You don't expect you to memorize all of these, but I do want to mention funders. Thank you to the National Science Foundation. We're just at the end of a 4-year grant that enabled us to do a lot of this work, and also Google gave us some money to try to make more public demos out of it, which we're almost at. So I gave a version of this talk last year when it was sort of the height of the Ebola scare. And people had heard things like this. I went and looked on Twitter, and there were tweets that Obama had plans to bring foreigners to the US for Ebola treatment, that the nurse from Dallas, Nina Pham, that her husband was hospitalized with Ebola symptoms, that there was an Ebola case in Michigan, and an Ebola case in Buffalo, and by all means you should avoid Wyoming, because everyone was going to go there to try to avoid it, and there were going to be a lot of disease vectors going to Wyoming. Sort of winging it here a little bit on our tech setup, so I think this is going to work better if I leave it up here. So what I want to talk about today, I want to tell you about some of the tools we've created. I'm going to give you an overview of a processing pipeline we have that is looking at, in the first stage, just looking at all the tweets that come in the Twitter fire hose, or actually we don't have the fire hose, but the garden hose, we see a fraction of the tweets that are coming in and try to find new controversial things that people are talking about that they might not have been talking about before. The second phase is retrieval. Once we have a potential rumor, can we get all the tweets that are either spreading or correcting it? And then the third one is, given those tweets, try to do something to help an analyst understand something about the audience that might have been exposed to it. So I'm going to go through an overview of that, and then I'm going to go into a little deeper dive on the detection and retrieval phases. So the basic idea is, as I've just described, the 3 stages. Rumor detection, and then interactive retrieval, where we're trying to get all of the tweets that are either spreading or correcting the rumor and tell and divide them up which are which, and we'll have a little bit of human labeling to help with that, but we'll try to keep that to a minimum. And then once we have the tweets, visualizing something about who has been exposed to those. So the detection phase, you can imagine that there's a whole bunch of tweets that are coming in, and we want to say, aha, people are talking about Greeks self-inflicting with HIV. Real rumor from a few years ago. I'll tell you more about it. We are trying to detect things like that, and then we have sort of a triage page. Some of the things that we detect will actually be interesting, controversial things that people are talking about. Some of them won't. And so this triage page is for people to come and look at and say, yep, this one's interesting and deserves to have some more attention. In the second stage, once we've decided this is something that might be worth attention, we want to try to find all of the tweets that are either spreading or correcting and automatically classify which is which. To do that, we're going to have some kind of labeling interface where we're going to select which tweets to show to people, and they're going to say, yes, this one's spreading the rumor, this one's correcting it, this one is not relevant to the topic at all. It was just a mistake of our retrieval system. And at the end of people labeling a bunch of those, we then have these piles of tweets. And then we want to do something to analyze who has seen all of these tweets, the diffusion process. So this one that I mentioned, this was in late 2013. The World Health Organization released a report that said that half of new cases of HIV in Greece were intentionally self-inflicted as a way to qualify for welfare benefits. After a few weeks, it was buried in the middle of a report. And after a few weeks, this got some notice and it caught fire on social media. In fact, it also caused the World Health Organization to notice that they had published this, which they didn't intend to publish at all. It was a mistake. They didn't. It was an error. I don't know exactly how they made that error, but they then sent out a retraction, and they said it was an editor error. There was no evidence that anyone, much less half the people, had done it. So when a rumor like that spreads, there are some questions we can ask, like how many people actually saw this? Maybe it just stayed buried in that report. Maybe there were 20 tweets about it. Maybe there were 200 tweets, but nobody was following the people who made the tweets. Or, conversely, maybe there was a big audience. How fast did it spread? How long did it take to go out? What percentage of the original audience that saw one of these tweets saw one of these? So was the correction reaching the right audience? And among those people who saw both of them, which did they subsequently tweet? You kind of hope that after you see both of those, you would, if you're going to tweet anything, you would tweet the correction, but not necessarily the case. So we call questions like that audience analysis. And we built a tool to support that. This is the visualization part. We do a couple things in this. First is we define a notion of the marginal impact of a single tweet, which is how many additional people who haven't previously been exposed to the rumor or the correction get that exposure as a result of this tweet going out. And then we show that the marginal impacts can be efficiently computed. And once we have the marginal impact of each of the individual tweets, we can do some nice visualizations to aggregate those marginal impacts and see in any given time period or for any given set of tweeters who, how, what impact do their tweets have on the audiences. Now, if any of you have looked at information visualization before, there's sort of a standard visualization, the network hairball. I made it nicer here than it would usually be. I used color to show correction versus the rumor. We showed arrows only for retweets, not for just follower relations. Otherwise, this would just be edges everywhere. We made the size of people's audiences, the number of followers that the tweeter had is the size of the circle. So having done those things, you can get something from this visualization. But it's pretty hard to make a lot of sense from it. You can kind of look at it and say, well, maybe there's more blue than red. But if really you just wanted to know how many people were exposed, like was there more blue than red, maybe this would be a better visualization. Just get a bar chart. So more people, it turns out, had at least one exposure to this rumor than the correction, but lots of people were exposed to the correction. Not so many to both, and we'll say more about that in a minute. Another way you could present it is just as a table. We developed another way of presenting it that we think reveals a little more information. So you think about this as tracking the states of exposure that people are in. So if many of you, I guess, are in security, or you're at least here at a tech talk, you've seen a state diagram before. So you can imagine at any given time, each person who's on Twitter is in one of these states. They've had no interaction with this meme at all, or maybe they follow somebody who has tweeted the rumor, or they follow somebody who's tweeted the correction, or they follow people who collectively have tweeted both. Maybe they actually got in the action themselves and they tweeted either the rumor or the correction or both. So if you think of each person as being in one of those states, then each tweet has a marginal impact of moving people between these states. So imagine that we have this little network of people who, this is actually showing the follower links, and then Bob tweets the rumor. That causes all the people who follow Bob to get moved into the exposure state. Now, I should caution, we don't know who reads all of their tweets. So I'm using as a shorthand exposed. What I really mean is potentially exposed. Yes?
Question for you. What about mutation of the rumor as it travels?
Yeah. There are lots of interesting other questions, like the exact form of the rumor. That first it was they're doing it to get benefits, and now it mutates to something else. We don't try to track that. We group all of the different versions. If our retrieval mechanism works well, we group all of those together and say they're part of the same diffusion. And if it gets far enough away so that it's HIV in Spain, then we just treat it as outside of what we're doing. But there are people who've done interesting things about trying to track the mutations of memes as they diffuse. That's not what we're doing here. I should also say what we're not doing here, we are not figuring out whether any of these rumors are true, which is a really good thing to try to do, just not the job that we're taking on. We're trying to understand the diffusion of these and what audiences they reach and what detect new ones that are coming. And so if you're asking where in the process are we figuring out whether it's true, we're not. So one tweet comes in, that moves a few people in one state. Now Alice tweets a correction. Bill follows Alice. So Bill is now moving into the exposed to correction state. Sarah also follows Alice, so she now has been exposed to both. And Alice, of course, has moved into the state of having tweeted the correction. So if you sort of aggregate this, you can think of these as flows that as a result of the collection of both of those tweets, we have a lot of people who went here, thicker arrow, not so many people who went here, thinner arrow. And just transforming this graph a little bit into another visual form of it. This is actually the same information, but has some nicer properties that I'm going to show you in a minute. This is called a Sankey diagram, first popularized with Napoleon's army going to Moscow and coming back, and a lot fewer people coming back. So we've got people starting in the no interaction state. Eventually, they get exposed to the room. Some get exposed to the rumor first. Some get exposed to the correction first. Some people get exposed to both, and so on. So this is the total number of people who are exposed. The people who are exposed to just the rumor, those are exposed who are at some point exposed to the rumors, at some point exposed to the correction, at some point exposed to both. And we can even see things like, of the people who were exposed to the rumor, how many of the people who tweeted the correction did that in response to seeing the rumor and realizing it must be wrong, as opposed to, well, they saw a correction and retweeted it. More people who were exposed to the rumor went on to tweet it than to tweet a correction. And we also can get time dynamics. And this allows you, as an analyst, to say, well, where in the timeline of the diffusion does most of the action of people getting exposed to the rumor or the correction happen? Can you cue up that video now? So at the bottom, there's a timeline, and he's dragging the slider across to make a bigger or smaller time window. And when he does that, the black portion gets bigger or smaller. So in this very short window up at the front, more than half of the exposures to the rumor are happening. And you can do things like also define a small window and then drag it across to find where interesting things happen, like how long did it take for half of the people who are going to get exposed to the correction to get exposed to it? Or was there a time period where the correction was reaching more people than the rumor was? Okay, so that's the kind of visual analysis that we're trying to get to. I'm going to spend much of the rest of the time let me just mention, so much of the rest of the time I'm going to talk about how do we get there. So first, with the marginal impacts, that black region that you saw of here's what happened in a particular time period is just the sum of the marginal impacts of all the tweets that happened in that period. So we have to compute that marginal impact. And the thing that makes it possible for that to be a real-time thing is that we pre-compute all of those. So we start with the follower list for each of the tweet authors, and then we essentially simulate one tweet at a time, keeping track of every ID's state of exposures. And so after each tweet, we can count how many people have changed to a different state of exposure. And so for each tweet, we then have 8 numbers indicating how many people did each of the transitions. And that's sufficient then to, you send all of those marginal impacts to the browser, and then the browser can do all of that animation in real time. We also have some supplemental views. I mentioned the network diagram. That's available. Or you can actually just sort of get the raw data. This is each of the tweets, and all of their marginal impacts as a column, and you can select subsets and if you're not a visual person, you can do the analysis that way. All right, so let me talk a little bit about the first 2 phases and what the technology is involved there, which is the detection phase and then the retrieval phase. So the detection phase, the problem is we don't know that people are going to be talking about HIV in Greece or some rumor related to a presidential candidate or whatever. And again, we're looking for these controversial, fact-checkable claims, not necessarily wrong, but things that are disputed. So it's sort of like the general trend detection problem in Twitter, that they have their emerging trends that they have on a front page, but we want only those trending topics that are disputed claims. So some people are just talking to each other. There's all these tweets out here, and some of these turn out to be rumors. And so maybe here's 2 explosions at the White House and Barack Obama is injured. This is a real rumor that went around a few years ago. We'd like to be able to pick that out. Now this is the graph of the tweet and retweet graph after 6 minutes. This one was originated by the AP. Somebody hacked into the AP's account and sent it out. So they had a big reach, and then it went viral. So that's after about 6 minutes. And of course, actually, yeah, that's about the stock market about that time. A brief drop there. So we would like to be just following the stream and notice when things like this happen, and we'd like to notice them as soon as possible. They won't all cause a stock market crash, but we'd like to get them quickly. And if you just start with what are the events that are happening and then try to classify, oh, is it a controversial fact-checkable claim, i.e. a rumor, it's not going to work so well, and I'll show you some evidence of that. But within 60 seconds, this is what it looked like, and there's enough information in there to detect at that point that there is some controversy about it, and these little blue nodes are the signals of that. I'll show you more in a minute. And basically, there are some tweets that have this special signal pattern, what we call inquiry tweets, and they tend to appear in some tweets for any rumor pretty early on. Not all the tweets, but somewhere, and we can then use those to say, hey, something is happening. So what are they? Well, it turns out there are some very simple things like people saying, is this true? Or what? This is the actual set of patterns we ended up using. So is that true? Is this true? Is it true? Some verification questions. They're not sure. They're asking. What? With question marks or exclamation points, or often a whole bunch of them. Real? Really? Unconfirmed? Or some things where they're actually straight out saying, this is a rumor, this has been debunked. So those are kind of correction type things, or that is not true, this is not true, it is not true. So this is sort of very simple text patterns. Yeah?
Did you craft those by hand?
Yeah, we crafted these by hand, basically by looking at a bunch of things and trying to find patterns. Now the trick is that we need to find patterns that are very specific. So if lots of things that are not of interest to us also have these text things in them, it's not going to be useful to us. They have to be early, and they have to be prevalent enough in the rumor memes. And so the student who did this is the work of Zhe Zhao, who's just finishing his doctorate this coming year, and he's trying to generalize this now and figure out what classes of things have some simple sets of patterns like this. So, with that, the idea is that there's a bunch of tweets about the explosion at the White House. Maybe only a few of them are going to have this inquiry pattern, but if we can find those early, and then kind of shake the Twitter stream and find the other tweets that are like it, that will be an effective way. So, some evidence. We have some data sets. One is from the time of the Boston Marathon. We did we gathered a bunch of tweets for the few weeks after that with queries that had anything to do with the Boston Marathon bombing. And then we also just ran it on the garden hose, which is 10% of all the tweets that are coming in. We ran that for 7 days. So using the inquiry plus correction signals, all of those 5 patterns, that's what we're saying is good. And then we have some other baselines that we're comparing it to. So one is to just use the trending topics that are mentioned on, make it to the Twitter front page and see which of those, and then take a subset of those, or follow popular hashtags. So sometimes people talk about hashtags as memes. So meme tracking is hashtag tracking. So of these, and we would do that and take up to 10 per hour for 72 hours, so 720 possibilities. Of those, only 71 turned out to be actual rumors as judged by people afterwards. Using only the correction signals. This is where people are saying, no, that's not true. This is a rumor, or I'm debunking this. We have to look at many fewer candidates, and about half of them are the things we're looking for. But if we use the inquiry and correction, we're able to get more things than we got with the non-specialized detector system. Now, the other thing about our detection system is that we don't have to look at every tweet and try to cluster it with all the other tweets that are coming in, which is, from an efficiency perspective, you just can't do that on the whole garden hose or the whole fire hose. So when we did our tests on the garden hose data set, we couldn't really compare it to these other techniques because they were just too inefficient to run. But running on that, we detected 92 good ones out of 350 candidates, which is a little more than a quarter. And our thinking is that a little more than a quarter is actually good enough to be a set of candidates that a human would then look at and say, yeah, this one is worth following up on, these 3 aren't worth following up on. 1/4 is a high enough precision there. Yes?
Sorry, I just wondered if you could quickly touch upon what is this inquiry and correction again? I followed the regular expressions, but what is this?
Yeah, exactly. It's the regular expression. So where did it go? Anything that matched the first 3 rows. I'm streaming this over the internet to get to there. So we probably lost our connection for a minute. The inquiry things are the patterns like, is this true? And the corrections are the patterns like, this is not true. So, this is not true, that's a correction. Inquiry or verification is this true? Questioning it. All right, now if I go on, is it gonna, it'll catch up with me eventually. So that's one claim about the effectiveness, that it's working better and faster, but it's also working earlier. So if you look at how early in the diffusion of one of these memes does somebody out there question it, it turns out it's usually very early. So it may still be spreading, but somebody is saying something skeptical. So here's the Boston Marathon bombing, and here's various rumors about it. And so for example, authorities ID a Saudi national as a suspect in the bombings. That one turned out not to be true. So that's happening on this timeline. And a little bit later, somebody put out a tweet that had one of the correction things, debunk, in it. But if we only wait for the debunk things, then we'd be detecting it later than if we notice this is the time when the first questioning tweet comes in. So we did we looked at a whole bunch of these and we figured out when did the first questioning thing come in and when did the first correction come in. And the questioning things came in pretty early, often within 10 minutes of the first tweet that was propagating something. I'm not going to go through all the details. Here's a whole bunch of these rumors. So in general, if you looked only for the correction signals when somebody is saying, no, this isn't true, you'd wait 4.3 hours longer on average. If you just used the trending topics, you'd wait 3.6 hours before it was a trending topic, but we would have gotten it much earlier, and 2.8 hours before a hashtag would be noticed. So the takeaway here is that these inquiry signals are very specific. When you find these inquiry signals, most often, well, or at least a quarter of the time, it's actually a rumor. And lots of rumors have some early inquiry tweets. In fact, more than you would, even many things that never become a trending topic. So given that we found something, people are talking about explosion at the White House, can we find all of the tweets that are mentioning that explosion? So this is, in information retrieval circles, what's called a high recall problem. Recall is, of all the things that match your query, what percentage of them did you find? Talk about precision as, of the things you found, how many of them were what you were looking for? So we want to get high recall. We want to find almost all of the tweets that are related, and we'd like to automatically create a classifier that will classify them as spreading or correcting. We can use people to label some of the tweets, but not thousands of them, because people will get bored. So the traditional methods for doing retrieval is that you have some kind of search engine, you put in a query, you get some stuff back, and then you do some kind of relevance feedback. Some of the things that come back, you say, yes, that's good. No, that one wasn't good. And you try to change the query as a result. So you make a new query, you discard the old query, and your new query you're hoping is better than the original one. And in iterative relevance feedback, you do that cycle more than one time. So that's sort of one approach that's been out there. And another approach is using what's called active learning, where you're creating a classifier and you're actively choosing which items will get labeled. So you start with the whole set of items available, and your computer program is picking which items to get some feedback on at each step, there are various algorithms that it can use to try to pick an item that will be very informative once the human labels it. Now, our solution is basically to combine those two ideas. That we're going to have an outer loop that does iteratively producing new queries, but then we'll have an inner loop where we're creating a classifier automatically, training it by having people label things. And I'll go through a little bit of, so here's an illustration. You're going to start, there's going to be an inner loop, and there's going to be an outer loop. The inner loop is creating the classifier, the outer loop is updating your queries. So you start, let's say, with some initial query. That gets sent to your search engine, and it retrieves a bunch of documents. And then you go into this inner loop. In this inner loop, not all of the documents will be reviewed by a person. So you have some kind of document selector algorithm that picks a subset of them, and those go to a person. That person then labels them. Yes, this is relevant. That's not relevant. This one is spreading the rumor. This one is correcting it. And then that labeled set then goes to another algorithm, the learner, whose job is to create a classifier or a ranker, something that can run on any other tweet and produce a score saying whether it's relevant or not and whether it's spreading or correcting. So you might give a few things to give 10 tweets to the person, they label them, you run your learner and you have a classifier, and you see whether that classifier is stable. That is, has anything changed in that classifier's classifications of the tweets that it knows about as a result of that? If it's not very stable, then it's probably a good idea to run this inner loop again. So we'll get some more documents. Oops. We'll get some more documents and have somebody label them, and then maybe we'll get to a point where this isn't improving things very much. So when it gets to be stable, it's not worth running the inner loop again, and we need to go get more documents, more tweets. Yeah, sorry, I'm going the wrong direction. So then we have a query generator that's going to go and take using the tweets that you've labeled so far, figure out what other tweets might be out there, what other keywords could be used to create a new query. So that updated query then goes to the search engine, and we do the whole thing again. And you do this some number of times, then you end up, because of the classifier down here, you end up getting very good precision. And because you accumulate a bunch of queries rather than replacing it each time, the query generator just needs to focus on recall. So the outer loop is able to focus on recall, and the inner loop on precision. So we ran this against, there are some data sets that are out there. There's this Trek, any of you know about the Trek competition? Text retrieval. So every year they have certain tasks, and they tend to be of the form, here's a whole bunch of items. Everybody, and here's your in English, your retrieval task, the set of items you're trying to get. The intelligence community likes this thing because they're trying to see whether people can find things that would be relevant to the intelligence community, for example. And a bunch of people submit their algorithms, and they take the top 50 or 100 answers from each of them, and they accumulate all of those items, and they give them to humans to judge them. So then they get a gold standard answer. Was this or that item relevant? It might be that there were more relevant items that none of the algorithms picked, and those won't ever get evaluated by a human. But anything that was picked by one of the algorithms as a top item gets evaluated, and then they do a little bake-off and see which of the programs did best. Of the things that they retrieved, how good were they? So we then come after, we actually participated in one of these, but I'm going to show you some results from things that we did after the fact, because then we had access to all of the items that had been labeled. In these kind of competitions, they use various metrics. I'm not going to go into too many details, but to give you a sense of it, if you're allowed to retrieve 50 items, then that would be R. I'm sorry, that's not R. In their whole data set, they have 121 items that they've marked as being relevant. That would be R. And then you're allowed to have your algorithm retrieve however many that is, 121. And the precision at R is how many of the 121 that you brought back were actually relevant. Another metric that's often used is called mean average precision. It's for things where your retrieval algorithm is returning an ordered list, and it gives you a better score if the ones at the top of your list are right than if the ones at the bottom of your list are right. Whereas this R precision doesn't pay attention to that. The mean average precision does pay attention to the order. So if any of you are involved in ever go to an information retrieval talk, you'll see some result like this. And the one that's the highest is always the one that the presenter created. We did really well here. That's the message. And it's not easy to convey this, but usually, like when people are comparing one technique to another, the improvement in R precision is like 0.02. And we got these giant giant differences. So this is doing qualitatively different than other techniques. Same thing if you use the metric that cares about order. We do really well. So when we did this in the live competition, we actually entered like 4 different variants of our thing, and we got the top 4 places in the competition. To get a little sense of how many labels do people have to give, we're generally finding something like 100 to 200. Then lets us retrieve the other 5,000. So it's not you don't get to just look at 5 tweets and then we're done. But you also don't have to look at 1,000. All right, so the conclusion from this is that we've got this retrieval framework that gets high recall without sacrificing precision. This is a general framework, and we've implemented it here for retrieving all the tweets related to a rumor, but there are some other settings where you might really want to have high recall, and we're working on some demos of that. And the demo we're working on now is medical literature retrieval. So, when I ask for what's the address of Duo security, Google gives me one answer and it's the right answer, I'm good. I don't need to have the other 110,000 places where the address is listed correctly. I just needed one because I just needed the fact. But there are other settings where you actually want you want the high recall, you want all of the examples. And so when you're doing academic literature review is one, when you're doing search of, you're trying to find all of the medical records that have some diagnosis, but where the diagnosis is not marked as a database field. When you're doing in legal cases where you got 100 boxes of papers and you're trying to find which of those is actually relevant. So we think that this general framework is helpful for any situation where you want the high recall. Oh, well, sorry. This is just making that point. Yeah, go ahead.
So you mentioned Google there. There's something implicit in what you said, which is that Google is the only result you need because it's the one that has a high reputation in your mind. I noticed that in the discussion of tweets, you didn't mention anything about reputational measures. I wonder if
yeah, I mean, I wasn't trying to make the point, although it helps that Google, they give me one and it's usually right. So that's the high reputation part. But my point is that once I had one, that's all I needed. I didn't need all of the documents that mentioned it. But there are other kinds of retrieval tasks where you do want all of the ones that mention it.
Sure.
Yeah, so I wasn't trying to make a point about the source being more reputable or less reputable.
My question was in your analysis of tweets and whether something is rumory or not, whether if reputational measures might help you determine, or sort of precondition the data set. Like the AP is less likely to tweet an unsubstantiated rumor than some random Joe.
Right. So certainly if you're trying to make some assessment of how likely is it that this is true, that would be really helpful. It might even be helpful for our task of just, is it a rumor at all? Is it disputed? And because there may be certain accounts that are just generating one after another. Think of sort of certain celebrity gossip accounts. So yeah, I think you could use that. There are some people who, there is work that people have done that's trying to use sort of the network structure, and this person's connected to somebody who's tweeted a lot of rumors in the past. Maybe that's another indicator.
So is Twitter the only place to detect rumors on the internet? Are there other social sources where you need to watch for rumors besides on Twitter?
Yes.
Can you give some
sorry,
examples?
yes, there are other places where it might be interesting to know where that rumors are spreading in lots of online communities, in Facebook, in LiveJournal, and blogging sites, and all kinds of other places. We're doing the academic thing of studying the thing that we have access to, and lots of the things where things actually, email would be another place that rumors are spreading, but we can't get access to people's emails. The strange phenomenon out there that lots of people are making their Twitter accounts public, and so even though my computer is not friends with any of them, it's able to scrape, and so it's a matter of convenience that's where we've looked.
Usenet is kind of no longer the place to look for these things.
Yeah, Usenet is not really, it's so popular that no one goes there anymore.
Yeah.
It died from its own popularity. Actually, every once in a while, I go back and check, and it's still there.
Yeah,
Yeah,
still there.
and it is public. Actually, around 2000 to 1996 to 2002, when people were doing research on online communities and they wanted to do it at big scale, they did it on Usenet. Yeah.
I had a question for you. I saw that you had a time domain analysis earlier on when you had your visualization. Did you find any relation to something being a rumor perhaps spreading faster than something that wasn't?
Do rumors spread faster than undisputed claims or other things that have similar eventual reach? It would be really interesting. That's the kind of thing we'd like to get to. In order to get to that, we need sort of a large collection of things that are rumors and a large collection of things that are not, that have otherwise, that reach about the same kind of audience. So I view this kind of as a step on the way to be able to do that kind of analysis. But so far, we've sort of cranked this machine from start to finish only for 9 rumors, I believe. So when we have 500 of them, and then we have 500 that are non-rumors but are some other interesting thing that spreads, then we could do that kind of analysis. But we can't do it yet. I will say, for the 9 that we've done it on, there's none of them where more people got the correction than the rumor, and there's none of them where a large fraction of the people who got there's none of them where most of the people who got the correction also got the rumor.
Is that what defines a rumor, maybe?
Maybe. I don't think so. I think something like this, the fact that there was so little overlap in the potential audience of the people who tweeted the rumor and the correction on that HIV thing, I think that's disturbing. So it's like there's one part of the Twitter sphere that is out there trying to correct things, and there's another part of the Twitter sphere that's not, and they have different audiences, and it's just like they're not the same people. Yeah.
So the HIV example, what you used, right? It's a multilingual thing. If you look at it, it's a Greek. Thank you. So that was like something regarding Greece, right? So what if the correction was in a Greek language? Would it be able to interpret that signal?
Yeah. I'm sure there was, in parallel, some diffusion of Greek tweets about this, and we did not pick those up because our
patterns, right? Patterns look very specific.
Our patterns are in English, and our humans who were looking at the tweets and saying yes or no could only read English and not Greek. You could use, it's not that you couldn't do it, we didn't do it.
Okay.
For the Greek tweets or the Chinese Weibo or the whatever the.
So I thought it was interesting. One of your slides you said real rumors, and you wrote real rumors.
I did. Sorry, I'm not sure. I don't know what I meant by that.
Well, I thought it was interesting because you didn't say fake truths. right? And I think that's kind of the distinction I think you're
I
getting
no,
at.
no, sorry. What I meant, now I remember where I would have used that. In our first phase, where we're using those text patterns and we're saying, okay, here's 10 things from yesterday that might have been rumors. When I say real, a human looked at it and said, oh, that's a collection of tweets that isn't a disputed factual claim. It's not that it's not that we said they're really true or not. It's just some of the candidates that our tool is surfacing aren't the things we were looking for. They aren't rumors. Does that make sense?
Yeah, but
Okay,
maybe that's
you were making a different point.
something different. I guess I was just thinking about the qualitative aspect versus quantitative, and I think with the patterns, when there is enough momentum behind these tweets, then there starts to be, some interest in it being a rumor, right? If just one person makes a false truth and it doesn't get spread, nobody's really concerned about it, even if it is, in fact, a rumor, right?
Yes. And so in that triage phase where the first tool with the text patterns and the clustering, that's managed to surface some candidate rumors, then people have to look at them, and they're not just going to look at them and say, is it a rumor or not? They're also going to say, is it a rumor I care about? And one of the reasons you might care is the topic, okay, it's a rumor about a celebrity, and I don't care whether that spreads or not, perhaps, but also, how many tweets have there been? There's only been 7. Perhaps it doesn't deserve our attention. Let's wait until there's 70.
Those of us in the security field know that there are rumors which eventually turn out to be true. That as people are burying the facts for some period of time to find they couldn't keep it buried anymore. So just because it's a rumor, or it shows to be a rumor, does not mean that, well, this is eventually be disputed, but it may well be later be confirmed.
Right. So, but the fact that it's disputed for a while is of interest, and so those are the ones that we're surfacing, and those are exactly the reasons why we're not trying to get in the game of deciding whether it's true, because you may just not be able to tell, given the facts that are publicly available today, whether it's true. And trying to do something like see how many people are saying it's plausible and how many people are saying it's not plausible might not be a very good way to tell whether it's true or not. So that's sort of part of why we're not getting in that game, is that we don't have a way of telling whether we're right or not when if we were to say this is true and this one isn't. Yeah.
So I don't use Twitter a whole lot, so I don't know if this is true or not. But does Twitter have a way of doing something like what eBay does? Like somebody was saying, giving weightage or reliability marks to people who have accounts on it.
Vote it up or down?
Yeah.
So this is sort of the reputation question that came
Exactly.
earlier. Yeah.
Yeah. So is that a recommendation you could take to Twitter? Because it seems like it's a big platform these days for everything, really. So.
There are some. So first of all, there are lots of signals that could be used, like how many followers do people have? So every day, people are making decisions. Do I follow that person? Do I not follow that person? Which are effectively reputation information that can be mined and that actually has been mined. There's a company called Clout that'll compute a Clout score for each person, which is based in part on how many followers they have and their Clout scores. In a sense, the fact that Twitter shows you how many followers everybody has, it is surfacing some of that. You could imagine something else, something that's more based on their behavior. But if we assume that those followers are in part a reflection of behavior, that may be sufficient to get the kind of thing that you're looking for.
So you're not using the follower metric when you're, in addition to the pattern thing, to find out this guy could be a more reliable candidate for a real rumor?
Yeah, we're not, because we're just trying to find those texts that somebody is disputing. So if nobody's disputing it, then or questioning it, it never comes to our attention. And once it does come to our attention, then the metrics we're using for trying to decide whether we want to do something more with it are not based on any kind of reputation. I'm a big fan of reputation systems, so if any of you look me up, I've written a lot about them, but just not something we used here.
Are you considering retweets that have been quoted by other people?
That have
'Cause
been
right
quoted?
Yeah, so right now you can retweet a tweet and you can quote it. So I could probably be a rumor, but I just write fake as a quote in that. So are you considering those in your data?
So you mean sort of a retweet that's not just hitting the retweet button, but that is
but
quoting it
quoting
and
it,
then
yeah.
slightly altering it.
Yeah.
Yeah, so those should get picked up in the retrieval process because
But
the text.
what would you consider it? Because are you reading the quote or are you actually reading the retweet itself? Because the retweet might be like a rumor and he's actually quoting that it's fake.
Yeah, so if somebody makes a new tweet that includes somebody else's, but then says he's all wrong, then our classifier should, if it's working well, pick up on the he's all wrong and mark it as a debunk. Whether it's accurate enough and whether the signals are available to always tell, that's another question. But that's what we're after is to group all of them together based on the content being similar, but then discern spread versus correction from giveaway words in the tweets.
So the instant messaging has taken on sort of like where you have acronyms like LOL and things like that. Do you think this Twitter platform can gravitate to something that says, debunk for getting? Is that how it works these days? You've used a couple of phrases, debunk and fake or something, right?
Yeah.
For the regular expression. Is that what it's gravitating
I think
towards in the
within
community?
particular sub-communities, phrases have developed.
I see.
We went looking early in this project. We figured, there's probably a community of people out there who are, just like the train spotters or the people who are just enthusiasts about different areas. And we'll find the people who just devote all of their hobby hours to finding out that somebody out there on the internet is spreading something that's wrong. And then if we could tap into those people, they'll be our labelers, they'll do all our work for us. And so I sent an undergraduate out, find your summer project, find me all of the hobbyists, the rumor spotting hobbyists. And she couldn't really find them, and it wasn't her fault. I think they really aren't there in that form. What there are is enthusiasts about Apple products. And so there's a Mac Rumors forum, and there's people who are, really interested in Republican presidential candidates, and they're tracking all the rumors about them. So there's a very topic-specific set of people, and they're not only following rumors, they're also doing other things related to that topic. So it made it a little bit harder for us to try to find these, to make this a general technique. Here comes, what do you call this thing?
Catchbox?
A catchbox. Is this homegrown technology, by the way?
I think we bought that.
You bought that? We need that. We
Have
need
you
it
looked at
ours.
other things like, you're talking about rumors and stuff, look at Snopes.com and try to compare, or is Snopes way too far down in the timeline to kind of meet what you're looking for?
Yeah, so that was our inspiration is, okay, places like Snopes exist and they have a network of people who feed them things. That would be our community. There's Snopes and there's one other it's like that. And so this undergraduate, asked, can I join the forum, the mailing list for I think it was Snopes, but it might have been the other site that I'm forgetting the name of. And after about 2 or 3 weeks of her sending repeated emails, they finally let her join. And she found out, well, the reason no one had let her join right away is that it was dead. People weren't talking to each other anymore. So I'm sorry, I got sidetracked. That wasn't really your question. Remind me of your question again.
I was just asking if if you guys used
Oh.
other data sources besides Twitter
Yeah.
to try to.
Right. So the other thing I'm giving you brain dump of various things we tried here, but we did try starting with factcheck.org and Snopes.com and these all have the sort of the structure that they have a page with somebody said this, we investigated it, and here's our assessment of whether it's true or not. So you're exactly right that it's way down the timeline. So by the time it gets to them and then they've had time to investigate, is it true or not, it's not in the range of things that, so like I did this because I wanted to find examples before we had this whole pipeline. And so I went and I tried one after another of the things that they had evaluated on factcheck.org. This was a couple years ago during congressional campaign, I think. I just went through one after the other, and there was nobody talking about any of them on Twitter. There was, pants on fire, pants on fire. Here's all these lies that the politicians are saying in their commercials, and I couldn't find anything on Twitter about them. But I think there might have been back at the time that they actually happened. So that I can't tell. And one of the things I want to do is, when we get this cranking, is I want to tell whether they're just writing about, they're generally writing about things that are either in advertisements or debates, or things that are talked about on CNN and MSNBC. Is it that the broadcast media is just talking about completely different political rumors than Twitter is, or is it a timing issue? My hunch is actually they're talking about different things, but I don't have data for that yet. We have to pass the box.
You were talking earlier about one of your collaborators came up with that set of filters that's kind of the initial piece in the pipelines that's like super important, and you said that he was working to generalize that. Can you talk a little bit about what that means? Is that more filters? Is that some heavy NLP machine learning algorithms? What kind of approach is he taking to better generalize that first piece in the pipeline?
Yeah. So there's his thesis proposals next week, so I'll be able to tell you better then. But I have talked to him, and I think there's two kinds of things he's trying to do. One is find more nails for his hammer, and the other is make the hammer a little bit better. So what you're talking about is, instead of these 5 patterns, could we do a much more sophisticated thing that would use NLP and do better? Yeah. So that would be making the hammer better. But I think he's also trying to see what other things besides detecting rumors have the property that there is some set of signals that are precise and early, but precise, early, and frequent enough that they're useful as detectors.
So actually, continuing on that, I was wondering if you considered maybe word-level n-gram analysis. That sort of thing works for malware pretty well.
Uh-huh. So word level, and so looking for patterns of 3 words or any n, but yeah. I'm trying to remember all of the different things that they've tried. Certainly in the second stage, when they're making the classifier, they've tried terms and bigrams as features that the classifier can use. I don't know if they've gone to 3 to trigrams or not. In Twitter, there's only 140 characters, and there's a lot of, but yeah, there may be cases where looking at multiple words in sequence could help. Is that getting at what you're asking? Yeah, I don't know what in this first phase of are there detector things. But I'd actually like him to get to this thing of, rather than having 5 hand-selected terms, that we ought to be able to learn a set of things that are even better detectors. And those could be trigrams, or they could be other kinds of features that you could look for.
That way, once you did have the Canada n-grams, I know that computationally that can be quite a bit, but even like 2 or 3 level for this, then you could have humans classify it, but then fall back on the n-grams to see which one of those actually signaled, and then maybe get the person out of the loop. Maybe.
I mean, essentially that's what this in the second stage, that's what the classifier in the inner loop is doing, right? We've got a bunch of features. A person looks at the items, they mark them yes, no, correction, spreading, and then we then go and try to figure the learning algorithm is figuring out which features are associated with a yes answer and which features are associated with a no answer. But in that case, it's specific to the particular rumor. So at the end, it's learned something, but it's only learned something that's helpful for detecting tweets about that rumor. It's allowed to have very topic-specific terms. Maybe there are things in the first stage, we're looking for things that are topic-independent. So it may be there that if we learned them once, then we wouldn't need the people again. Throw the box up front. I thought you had your hand up. No? Oh, I'm sorry. I think that's probably good. Oh, we got one more.
Ready?
One more might as well. Looking at geography, you're studying the Greece one, and the Greece one had this type of pattern. You've done 9 of them. Is there anything that you can point to saying that maybe in the U.S. there's more retweets of the real things, or outside of the U.S., or looked at how quickly they rumors spread across boundaries?
I would love to. 9 is not enough to detect a pattern. Sorry. I'm not trying to put you off. You're asking exactly the right question. In some sense, the kinds of questions that we asked 5 years ago, and realized we just couldn't answer because it was so hard to build up a corpus of rumors, and so we ended up instead building a whole lot of machinery for building a corpus. And the next round will let us do the substantive analyses. Great. So let's wrap it up here. You guys all got to drink beer beforehand, but maybe now I'll get to. And if people want to stick around for a minute, I'd love to meet you.